Welcome back to the classical universe. In the last video, we saw that energy is quantized in solar systems in the exact same way it is quantized in atoms. That is, for an atom, the energy of an electron is given by E0 times Z squared over N squared using the Bohr model, and the E0 times alpha squared over N squared for planets in a solar system using the same Bohr approach. We also saw that, by using the more general approach that I presented, the energy of the electron is rather E0 times Z over N and E0 times alpha over N for planets, and we demonstrated that these energy formulas from the Bohr approach were actually subsets of these ones, making these formulas the more general formulas for the energy of electrons and planets respectively. What we have been doing so far has been focused on atomic physics. Let us now extend this reasoning to develop the quantum mechanical model of celestial objects, which will directly show us how to correct quantum mechanics for subatomic and atomic particles and eradicate the weird interpretations and paradoxes. The very fundamental ideas of quantum mechanics are the ideas of wave-particle duality introduced by de Broglie and the quantization of energy introduced by Max Planck, which were later used by Erwin Schrodinger to develop the Schrodinger equation, which now stands as the pillar of quantum mechanics. Before we extend these ideas to solar systems, it is important to understand how they came about. Before we dive into the history, please subscribe if you are new to this channel, and if you enjoy the video, please enable to give it a thumbs up. It all started with the question, what is light? Democritus around the 5th century BC and Euclid postulated that light was made up of tiny indivisible particles. By the 2nd century after the death of Christ, another man came along and described light as a wave. His name was Plutarch. He studied the reflection of light by spherical mirrors and could explain using the reflection idea of light the formation of images. There was not enough data to conclude whether light was a wave or a particle. In 1670, Isaac Newton came along. He argued that the perfectly straight lines of reflection of light could only mean that light was made up of particles. But just a few decades later, Thomas Young performed the double slit experiment and observed that light could undergo diffraction and interference, characteristics which only waves could show. In 1901, Max Planck postulated that the frequency of the light emitted by a hot body was equal to the frequency of the oscillators producing the light. These oscillators were the atoms of the hot body. More precisely, the frequency of the orbiting electrons. He also stated that these frequencies were directly proportional to the energy of the oscillators, and the constant of proportionality was later measured and it is now known as the Planck's constant. Therefore, he wrote E equal to hf, where h is the Planck's constant and f is the frequency of the oscillators. This shows that the energy of the atoms were quantized. Since the light they produce have the same frequency, Albert Einstein argued that it means the energy of the emitted radiations will also have energies given by E equals hf, meaning that the energy of the radiations was quantized as well. This was proven to be true by the photoelectric effect, where it was shown that the higher the frequency of the light incident on a metal surface, the greater the kinetic energy of the emitted electrons. This once again suggested that light was made of particles which were later called photons. Einstein said the energy of one photon was equal to Planck's constant times the frequency, and this energy was called quanta. The story keeps getting interesting. A few years later, a French physicist by the name Louis de Broglie postulated that since light, which was a wave, could behave like particles, then perhaps electrons, which were particles, could also behave like waves. So he wrote the famous de Broglie equation, wavelength equal to Planck's constant over momentum. This means any moving particle with momentum should have a corresponding wavelength lambda. This idea was tested using electrons, which were at the time known to be particles. The double-slit experiment was performed using electrons, and the electrons showed an interference pattern just like waves. It was therefore concluded that matter exhibits both wave and particle behaviors, and this was termed the wave-particle duality of matter. This equation and the Planck-Einstein equation form the basis of the Schrodinger equation. Ernst Schrodinger used them to develop the Schrodinger equation, which today is the key equation in quantum mechanics. He introduced the complex function psi, which is called the wave function, and it is thought to carry all the information that there is about a particle, even though this function has no physical meaning. Notice that the two equations, which are the key equations of quantum mechanics, came about by educative guests and have no theoretical derivations. Planck guessed his E=hf equation out of frustration, and de Broglie did almost the same thing. This is why there are a lot of problems explaining quantum mechanics, because physicists themselves don't even understand the equations or how they came about in the real sense. Today, I will derive those two fundamental equations in a very clear and understandable way, and as a bonus, show you how these are the same equations for both electrons and planets, or I can say atomic and cosmic objects. So buckle up and let's go. Remember, if you are new, please subscribe. And if you like the video, please endeavor to press that like button and share the video with your friends. Understanding waves is crucial to understanding quantum mechanics. So let's take a second to look at waves. Let's take a tire rotating freely in space. This is an example of a perfect circle of radius r rotating about its center with angular velocity omega. A point on this tire is equivalent to a point going round a circle. Let us define this particle's position at a particular instant where the particle has made an angle theta with the x-axis. Using a coordinate system whose origin is at the center of the circle, we see that the horizontal displacement of the particle x is given as r cos theta, and the vertical displacement y is given as r sin theta. These are equations of a standing wave, in which, as you can see, the tire is not moving. If we let the tire now touch a rough surface at an instant where the particle is directly above the center, the tire will move a horizontal distance delta x in some small time delta t, while it rotates with the same angular velocity omega. The horizontal distance covered by the tire delta x is equal to the length of the arc bounded by the initial and the final points of the particle. At this new position, the particle now makes a new angle with the x-axis. Let's represent it by theta 2 and the initial angle by theta 1. The difference in the angles, which is equal to the angle covered by the particle, is given by theta 1 minus theta 2. Therefore, theta 2 is equal to theta 1 minus delta theta. The vertical displacement of the particle in the first instant is given by y1 equal to r sin theta 1, and the vertical displacement for the new position is given by y2 equal to r sine theta 2. But theta 2 is equal to theta 1 minus delta theta. Therefore, y2 is equal to r sine theta 1 minus delta theta. Recall that angular velocity is defined as the change in angle per unit time. This means that delta theta is equal to omega t. Hence, this equation becomes y equal to r sine theta 1 minus omega t. If the tire was moving to the left, the new angle will be greater than the old one, and therefore theta 2 would have been theta 1 plus delta theta. The corresponding displacement equation will be y equal to r sine theta 1 plus omega t. These are the wave equations for waves traveling to the right and to the left respectively, as clearly seen by the motion of the tire. So, the movement of the tire is apparently an example of a traveling wave and can be visualized as follows. How do we calculate the horizontal distance traveled by the tire in this time? This is the same as the length of the arc of the circle between the initial and the final positions. A circle can be modeled as many infinitesimally small line segments connected together, and the length of the arc is equal to the sum of the lengths of all the line segments between any 2 points on the circle. The length of one line segment delta s is given by the square root of delta x squared plus delta y squared. Factorizing out delta x squared, we have the following. To get the total length, we sum over the 2 points as follows. From the equation of a circle centered at the origin, y is equal to the square root of r squared minus x squared. So, dy dx is equal to minus x over square root of r squared minus x squared. The square of this equation gives this. 1 plus this squared gives r squared over r squared minus x squared. Subbing this in our integral yields this. We can factorize out r from the denominator to have this. We shall use the substitution x equal to r sine theta. By differentiating this with respect to theta, we have dx equal to r cos theta d theta. Subbing all this into the integral, we have this. Using the trigonometric identity 1 minus sine squared of theta equal to cos squared of theta, this yields s equal to the integral of r d theta, and this simply gives r times theta. But from the identity we used, theta is equal to the sine inverse of x over r. So s is equal to this, including the limits of integration. Assuming the particle has moved as follows, then the integral is from 0 to r, and this gives s equal to r times pi on 2 minus pi. This is equal to pi r over 2, which is a quarter of the circumference of the circle. So it means that for a full cycle, this distance will be 4 times this value, which will be 2 pi r, which is equal to the circumference of the circle. This kind of motion and that which is executed by planets and electrons are the same. So the motion of planets and electrons is wave-like. For one complete revolution, we have the following representation. As we have seen, the horizontal distance covered by the tire is equal to the circumference of the tire, which is 2 pi r. We have established that this is a wave motion, and therefore, by definition, the distance covered by this one cycle is called the wavelength, and is equal to the circumference of the circle, 2 pi r. Let us bring this to the solar system, but don't forget that this same analysis can be done for atoms. The wavelength of the planet is given by this equation, but r differs for different planets. That is, r is dependent on the orbital quantum number n. As a result, the wavelength is also dependent on the quantum number. So we write lambda subscript n equal to 2 pi r subscript n. The radius of an orbit is given by the following equation. So the wavelength becomes 2 pi times this. Cancelling out 2 pi yields this. This shows that wavelength is quantized in solar systems, which means that planets can only occupy orbits that are in a whole number multiple of some constant. Linear momentum is defined as mass times linear velocity. The linear velocity of a planet is given by the following equation. Subbing this in here produces this. This also shows that linear momentum is quantized. The ratio of the analogous Planck's constant to the linear momentum yields the following expression. Multiplying both sides of the equation by the square root of n alpha yields the following red expression. We see that the term on the right is equal to the wavelength of the planet, and therefore we can write p subscript n equal to square root of n alpha g on lambda, or lambda n equal to the square root of n alpha g on Pn. For a free planet, that is a planet no longer bound to a star, the idea of solar and quantum numbers become irrelevant. Since the square root of n alpha is just a number, we can absorb it into the wavelength and have lambda equal to this. So we can write lambda equal to g over p. This is the de Broglie equation for celestial objects. Remember the equivalence of g and h. So for atomic particles, we can write lambda equals h on p, which is the de Broglie equation as you know it. So lambda is the wavelength that you will measure for that particle in the lab. And when you measure it, you will have no knowledge of the orbit the particle came from. This makes the equation h over p appropriate. Looking back on our tire problem, the horizontal distance s covered by this tire when it makes one revolution is equal to the wavelength of the wave. And as we have seen, this is the same as the circumference of the circle. According to elementary mechanics, the translational velocity is given by the distance traveled divided by the time taken. The time taken to make one complete revolution is called the period. So, the velocity can be written as lambda over t. Frequency can be defined as the number of times something occurs in a given time. For a rotating body, this translates to the number of revolutions made per unit time. For one revolution, the time taken is equal to the period, so frequency can be written as 1 over t. So the velocity of the tire can be written as lambda times f. This means that the wavelength of the wave is given as v on f. Putting this into the de Broglie equation yields this. Cross-multiplying produces the following popular expression where f is the observed frequency. That is the frequency that will be measured in the lab, and it is related to the orbital frequency as follows. The unit of P times V is the unit of energy, which is the joules. So the term PV is energy. Therefore, our popular expression becomes E equal to GF. This is the Planck-Einstein equation for celestial bodies. It cannot be a coincidence that all the equations for solar systems we have derived so far have the same form as those of atoms. This is telling us that atoms are structured like mini solar systems. This is the beginning of quantum mechanics of the cosmos. So, click on that subscribe button. Let's continue. To watch the previous videos on this, go to the playlist titled Quantum Gravity by simply clicking on my channel profile below. The videos are in a chronological order. Thanks for watching and see you next time.